Okay, so I think okay, YouTube is finally like real life. Okay, so we get started with miniature number 25, which is about apparently turning a ladder over a finite field. And I think the context for the title is that the problem is motivated from a ladder turning problem that makes more sense in probably a regular field or in the more continuous setting. So let me just describe the source problem. I think the miniature has a nice construction in the continuous case, which I'm going to skip in the interest of time. But if you're as fascinated by the claim as I am, you'll probably want to go and read it. So what's going on here? So a Kakeya set is a set of points, let's say in Euclidean space, which contains a unit line segment in every direction. So if I just had to come up with a collection of points that contains a unit segment in every possible direction, what would be a very natural set of points to propose? A circle, perfect. So like if you picked up a unit circle, for instance, then and I suppose when we say unit circle, we mean not just the boundary, but everything inside it as well, the whole solid region. Then you can give me any direction you like, and you will find that you can actually there's a natural line unit segment in that direction that's rooted at the origin, but you can actually find many more because you probably have this whole um, the diameter line connecting the sort of antipodal points in that direction. You can move your segment along that line anywhere you like. So you have actually many, many unit line segments in every direction. If you were to take the circle of radius 1, I don't know if you could push your luck to a circle of radius half. Would that still work? So I'm not sure if when you say unit circle, if you meant diameter 1 already, but I interpreted that as radius 1. But suppose we shrink the radius to half, would that still be reasonable? Because like I said, with the unit circle, you have all this extra degree of freedom, but we only need one unit segment in each direction. So you could tighten it up to the circle with radius half and it would still work, but now you have no wiggle room at all, right? So speaking of wiggle room, here is a more challenging a more challenging requirement, the so-called Kakeya needle set, which is a Kakeya set, first of all. But not only do you have that you can accommodate a unit line segment in any direction, but that somehow these witness line segments are kind of connectable through a smooth set of operations. So essentially, you can start with a unit line segment in some direction, and you can rotate it continuously through 180 degrees to basically flip the direction of the unit segment, right? And in our disk with radius half, can we do this? Is it also a needle set? Oh, is it? Oh, okay. So let's see. Well, I guess it depends on which line segment you're considering. Okay, maybe let's see if we can draw the shape. Um, it's not really prepared for this, but okay. Where are my shapes? Okay, this is, let's say, a disk of radius half or diameter 1. And now hopefully it'll let me draw some kind of a straight line, which we have to now pretend goes through the origin. This is clearly not going through the origin. Okay, let's pretend this one goes through the origin. And okay, your problems with the orientation. Okay, I didn't think that far. But okay, I want to change the color of this guy. I can't. Okay, never mind. Okay, this is, let's say, a unit segment through the origin. If you really imagine that that's a needle and you place your finger somewhere here, you place your finger on the origin and rotate the needle 180 degrees. Would that not work? I mean, wouldn't that stay within the disk throughout? So it's not going to slip out and you've managed to rotate it. Now, this orientation business is okay. I'm not even well. Basically, the point is that if you labeled these 2 points, I think this is all that they mean. if I'm not wrong. So if you label these 2 points, blue and red, if you rotate this 180 degrees, then basically the blue and red would have swapped places. That's all that we mean. So is that fair? Yeah, cool. Okay, so this is, yeah, so this is all we are saying. So the disk of radius half is also a Kakeya needle set, because you can do this cool thing here. One question that people got interested in is, well, can you have a smaller region, a region with a smaller area, which continues to have this property? And at least with my very limited imagination, I figured that this seemed like such a natural thing to do. That I figured I'd be surprised if you can squeeze in, because it seems like, well, I mean, you start with a unit, with a needle of unit length, and if you have to rotate it, I mean, okay, I think the limiting factor in my imagination was that I was assuming that you have to pin it down somewhere and then rotate it, and then you end up, the locus of all of these points ends up basically shading out a unit disk, right? But you could, your rotations could be more imaginative, I suppose. So does anybody think that there's another smaller region that still allows for a unit needle to be moved around in this fashion? So by the way, for the record, Matuchek in the miniature says that he doesn't like the needle formulation, because he's like, why would anybody want to play around with a needle like that? So he thinks the more natural modeling of this puzzle is with this ladder and field terminology. So imagine that you own a field which is in a certain shape, and the question is, what's the largest ladder that you can fit in the field that you can maneuver however you want? So yeah, or you could think of it as, I think there's also a famous sofa problem, which is, I think, what's the longest sofa that you can turn around a corridor, given a corridor of fixed dimensions. So I think that's a problem in a similar spirit. But yeah, does anybody want to hedge a bet, especially if you haven't seen this before, on whether you can come up with a smaller region to accommodate a Kakeya needle or a ladder? Okay, maybe this is not an easy thing to just guess, so maybe not a very fair question. But if you look at the picture in the miniature, there's a picture of I think what is called a deltoid. At least I found animated version of the picture on the Wikipedia page on Kakeya sets. So this is what they seem to call a deltoid, and here is something that's well, I don't know. You probably have to do some calculation to figure out if you're better off than the disk with radius half when you do this. So this is, yeah, I don't know what the measurements are around. Well, I suppose, okay, I don't know if I can actually pause this, apparently not. But anyway, the inner circle is kind of tracing the, I guess now we're not rotating about a point, but we are rotating in some sense along this circle that's inscribed in the deltoid. And I guess, I don't know. So this is a cleverer construction, which we claim takes up less area compared to the disk with radius half. And you could ask yourself if you can do even better. Can you push your luck further? And I think the very surprising result that is known is that there's no lower bound. You cannot say that, well, any Kakeya needle set must have area at least something, because there is like, if you propose that, there is a construction that you can push to a certain number of steps, and it will end up beating whatever bound you claimed on the area. So this is, I don't even know, honestly, if I fully understand what's happening here, because the statement totally blows my mind. And in the miniature, there's some gossip about how, it sounds like a recreational math problem, but it's in fact a quote unquote serious problem that's been studied in harmonic analysis and blah, blah, blah. So anyway, there's some very interesting backstory to the main thing that we're going to get to, but this is all that I'll say about it. Like I said, it feels like one of those totally crazy things. And I think I have some very, very high level intuition for the construction, but not quite. So certainly not enough for me to present it. And my excuse is that we won't have enough time to go over everything. But There is a construction justifying what I just said, that there's no lower bound on the area of a Kakeya set. And the question has been asked, analogous questions have been asked in various other settings, and we are going to be looking at one of these other settings, which is the finite field in the title. So basically, instead of working in Euclidean space, we now work in a more discrete setting. So, but the spirit remains the same. So we are looking at Kakeya sets, which basically accommodate lines in every direction, right? So our underlying space now is Fn, where F is some finite field. And what we want is that you have, it's a Kakeya set if there is a line in every direction. And for us, a direction is basically, okay, so this is a question, right? What's a direction in Fn? In at least Euclidean space, we have some intuitive notion of, oh, these are all the directions. You maybe, take a walk around your unit circle and, you experience all the directions that there are. So what are directions here? We basically, I think it will be convenient, perhaps, to think of directions as essentially being, this component here, this t times u. So if you fix a vector u in Fn and look at the line which is t times u. So a line is basically a collection of points of this kind. Okay, so that's a plus tu is a line. Again, we are basically trying to mimic standard notions of lines and directions that we know from more familiar settings like the Euclidean space. But maybe, these are the images that I was trying to pull in very last minute, so I don't know if they're visible. But okay, here is a concrete space. What is this? This is n equals 2, and the field is FQ. So maybe I should write that down. So n is 2 and f is f sub 5. So that is the field with the elements 0, 1, 2, 3, 4. So for instance, here you have 0, 0. Now I don't know if I can move that around or not, but okay, apparently not. So okay, I'm not going to label everything, but just for reference, this is 0, 0. This should be 4, 4. And let me just go over some of the directions that we have. Okay, so this is one of the directions. I think this is everything with 0 on the first coordinate. So that's one of the lines that we have that determines a direction. And basically, you can imagine that all the other scaling, all the other translates of this. So if I do a x plus this guy, right? So if I shift everything, let's say 1 to the right, that's the same direction for me, right? So that's not a new direction. It's a new line, but it's not a new direction. Here is, however, a new direction. This is everything where the second coordinate is 0. So this was where everything had a first coordinate 0. Here, everything has the second coordinate 0. This is another one, which is, well, again, this looks like the standard y equals x line, but here that's going to be, whatever this is going to be, basically a comma a, right? In this language, hopefully this is clear. What would this be? I can pick u to be 1 comma 1, right? So t times u would be, what are my choices for t? 0, 1, 2, 3, and 4, right? That's my field, 0, 1, 2, 3, 4. If I pick u to be 1 comma 1, then all the points on that line is going to be 0 will give me 0, 0, 1 will give me 1, 1, 2 will give me 2, 2, and so on. So that's this line. This is another line. I don't know, I generated this with a script, so I have no intuition for what line this is, but okay, it's some line. See, I don't know if you can cleanly identify this as something. It should be doable. What is this guy here? Okay, I'm doing row column. So what is this? 3 or 4. Okay, any guesses as to what line this is? Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay, any guesses as to what line this is? Hmm. Okay,
Yeah, that should be 4-2, I think.
Oops.
Not 4-3. Yeah.
Indeed. Thank you. But this is 3-4, right? Yeah, I think that's 3-4. Got carried away with some hope for symmetry. So this is 4-2. Yeah. Thank you. Also remember we are doing mod 5. And yeah, so when you multiply something, so for instance, if I was to say something like 1,2 multiplied by 4, for instance, that would give me 4 and 3.
And that it's not 1,2.
This is also not 1,2. Yes. Thank you.
It's 1,3.
Indeed. Thank you. This is not 1,2. This is 1,3. Hopefully this is 2,1. I should have, yeah.
Yeah. So if you just go through 2,1, then you get 4,2, then you get 6,3, but 6,3 is the same as 1,3 because you're doing mod 5. Yeah.
So yeah, perfect. So we start with 2,1 and then 3, but hopefully this will go through. So 6. When I multiply 2,1 with 3, I get 6,3, but that's going to be 1,3. And when I multiply 2,1 with 4, I get 8,4, but 8 is 3 because we're going mod 5, and so 3,4, and then of course we still have 0 when you multiply by 0. So you get the origin for free in most of these cases. So yay, okay, so this is a line, and this is distinct from, well, I guess you just have to trust me on that. These lines were generated in a way that they're all distinct directions. They're not translates of each other. This is the last one. I suppose there is some symmetry to this, and so if you write it out, you'll be able to, yeah, you should be able to see that there is a line underlying this as well. Yes, Jagdish, thanks. I think that was a correction that we hopefully eventually made. And yeah, so this is these are examples of the how many did we do? Okay, this is one more. This is one more direction. And so we saw, I think, so 6 directions. This is a field with 5 elements, and it turns out that there are 6 directions. That's kind of natural given the way I said we can think about directions. Basically, okay, maybe it's, okay, so maybe I shouldn't say it's terribly natural, but if you imagine that these, other than the 0 point, right, the rest of these actually end up falling in different buckets. Okay, it would be nice if somebody has an intuitive argument for why we are seeing in this example 6 directions, and in general, if you're doing especially with n equals 2, right, and you're doing FQ, you're going to see Q plus 1 directions. I think I have some very hand wavy thing about, well, you have Q squared minus 1 points, and each of these lines other than 0, 0 have Q minus 1 points on them. So they sort of get partitioned into Q plus 1 buckets. But I think that still leaves, the reason I'm saying that's hand wavy is because, well, I think, you would still have to say things like, well, these are the only directions that exist. But if you come up with some other subset of points which form a line, you can in fact realize it as a translate of something that we have already seen. So I think that requires an argument. But okay, so the number of directions is not going to play an important role in what we are going to see. So I'm going to let this be. But if somebody has, if it's somehow immediate to somebody, then let me know, because it wasn't obvious to me. But yeah, you can count. Yes.
There's a hand wavy proof. Hand wavy proof is that I think along the x-axis, if you just focus on the x-axis, right? Okay. And you take any of your u and then you keep adding and keep going around. It's essentially like an arithmetic progression, but because of GCDs and various other things, it will happen that you will pick up a red point on a column every time.
I see. Okay.
Right? So you can't escape being in every column once. I mean, there can't be a gap.
Right. Okay.
Because of some GCD happening somewhere. Yeah.
Right. Fair enough.
Yeah. So effectively, it's enough if you just pick up the points on that on a specific row or column. And
correct. Yeah, I think somehow those become, in some sense, representative elements of your directions. Yeah, and then everything else gets filled out. Yes, and I think yeah, somewhere the fact that we're working with a field is going to help us with arguing this. I suppose all bets are off if the underlying thing is like, instead of 5, if I had 6 things here, you probably run into some kind of trouble. I'm not sure, but yeah, okay. So
the handy part was 5 is okay, but
yeah,
what happens when you have 9?
correct. The GCD bit, yeah, I think that does play a role. The bit that you said about the arithmetic progressions, that you get a clean partition and you don't run into.
No, it's probably a finite field, so it can be a prime power. Answering Jagdish, yeah.
Right.
It can be a prime power, yeah.
Yeah.
So 9 is possible, or 25 is possible. Then I don't know.
Yes.
Yeah. Okay.
Exactly. Yeah. So with 9, actually, we shouldn't get into trouble, but potentially when you have, I don't know, these are they called zero divisors or something, you might run into. I don't know, you might run into some corner cases. So I think this one is worth.
No, the field will not have zero divisors. That's not the issue.
Field will not. Yeah, exactly. A field will not. So this is my point, that the assumption that we are working over a field is perhaps important for this counting argument.
Yeah, it's important, but I just don't see what happens if you have 8 or 16 or 25 or something. Yeah.
Yeah.
Anyway, yeah.
It's not immediate. So for all I'm not sure. Maybe this one's not contingent, but yeah, it's probably worth. I think the intuition that you were just sharing, I mean, it makes a lot of sense. I mean, enough sense that we should be able to probably convert it into something that has a little bit more notation and actually checks out. So yeah, that's food for thought. But yeah, let's say we have a bunch of directions, yeah, this is just bringing back the definition of a Kakeya set over a finite field. And the question we ask again is, how small can it be? In the real setting, we said it can be as small as you want, but here it turns out that there is in fact a lower bound. And there was supposed to be, I mean, I was trying to include a warm-up example in F2, but let me just skip ahead to the main result here. So the point is that there is a substantial lower bound. So if you want to be a Kakeya set over Fn, then you have like a substantial fraction of the full space of points. So this is q plus n choose n would roughly be something like so yeah, the total number of elements in Fn is like q to the n, right? And yeah, you can try to work out some approximations for this binomial to see that you're actually, like any Kakeya set, is picking up a substantial fraction of this q to the n. So we want to argue this, that you must have a lot of elements if you want to accommodate a line in every direction. And let's maybe go ahead and try to show this. Are there any questions about the claim that we are making? I know it says conjecture. This is verbatim from the miniature. It turns out that I think this was proposed at some point, that in the finite field setting, you will have a lower bound of sorts, unlike the real analog. And I think it was open for a little over a decade or maybe even more. And then there was this very slick proof based on what's called the polynomial method, which we are about to see. And I think the only complaint that people have about this proof, as far as I could find out, is that it doesn't shed any light on the structure of Kakeya sets, because it feels like one of these existential, arguments by contradiction. So you don't get any structural insights, but there's some, magic that makes things work. So So I'm just going to go ahead and try and present the main argument that goes into proving this statement. But it turns out that there's just lots and lots that has been studied around these structures. So if this sparks some curiosity, you'll have a field day going down these rabbit holes. So, okay, for some reason, my notifications seem to be going off. Let me see if I can fix that. Okay, good. So, yeah, any questions about the statement? Is the statement clear? Give me a +1 if we can move on to the proof. Okay, thank you. All right, so we're going to make use of this lemma, which I will come back to at the end. But essentially, this seems like this is probably a nice thing to contrast with what we have seen with Schwarzschild maybe. But anyway, so suppose we have a multivariate polynomial of degree at most t. Suppose we have, in this case, actually, suppose we have a small number of points. We can always construct a multivariate polynomial that vanishes on all those points. Okay, so these are n points sitting in Fn, and notice that this n is small. It's bounded above by d plus n choose n. So if you give me a small number of points, I can always construct a polynomial that vanishes on all of those points. Okay, you just have to give me a small enough set. If you give me a small enough set, depending on the set, maybe a different polynomial every time. Different sets will have different polynomials that witness this property. But the cool thing is that this is like, think of it as a magic trick, where the audience proposes a set of points and you pull out of the hat a degree d polynomial, which happens to just vanish on all of those points. Okay, so we are going to make use of this lemma to prove the main theorem. Okay, so this is what we want to show, and let's see. Let's say that we manage to construct a Kakeya set which is smaller than the claim that's made in the lower bound. So suppose you have a Kakeya set which has less than n plus q minus 1 choose n elements. Now, I'm going to plug in this lemma here. So remember here that n is of this form, n is less than d plus n choose n. So I'm going to say that because this is, I'm going to think of this k. So remember k is from where? These are all points in Fn. Okay, these are all points in Fn. So I have a small set of points in Fn. So I can create a polynomial that vanishes on all points in K. And I can create a polynomial of degree at most Q minus 1. That's just by pattern matching the lemma with this bound. Okay, so remember that if you give me points in Fn, where the number of points is strictly less than d plus n choose n, then I can give you a polynomial of degree at most d, which vanishes on all these points. Yes, so d plus n choose n. So here I have q minus 1 plus n choose n. So q minus 1 is my degree bound. Agreed? +1? Yeah, I can use, and I'm just plugging in the lemma. Just believe the lemma is a black box for now. We'll come back to it. But plugging in the lemma here, I have a small set of points, so I can create a polynomial that vanishes at exactly those points. This is a multivariate polynomial in n variables and degree at most q minus 1. So the lemma basically said d plus n choose n. If you give me fewer than these many points, I can give you a polynomial whose degree is at most d. So we're basically plugging in d equals q minus 1. So let me know if this makes sense. Okay, all right, thank you. Abhinav, is anything confusing about the statement to the others, or do you think I can move on? So if anything's confusing either about the notation or the statement of the lemma, like I said, I'm not asking you to assume or believe the lemma. That's something that we are going to I figured it would be nicer to just prove that at the end, but we're going to use that as a tool going forward. So okay, in English, let's just remember this small number of points. I can come up with a low degree polynomial that vanishes on all those points. And I think that tension between how small the number of points are and how low the degree of the polynomial is, that sort of matters. Because if you were, I mean, that's what makes the result interesting, I think, of the lemma. Because I suppose if you're allowed to work with an arbitrarily high degree polynomial, then you can sort of fit, you can freely fit it, right? So that's not, I mean, you give me like 100 points on which something should vanish. So I'm just going to write whatever, x minus the first point times x minus the second point and so on. I can do that, but then that blows up the degree in a way that's proportional to the number of points. So the cool thing here is that I do have a small number of points, but still quite a few relative to the degree. That's what makes this lemma non-trivial or interesting or not obvious or whatever. But we plug that in and say that, okay, you think you can give me a small Kakeya set. I'm going to start my journey of coming up with a contradiction by saying, well, let me first construct this polynomial from the lemma, which has low degree and vanishes on your entire set. And I'm going to use this polynomial to come up with some kind of a contradiction. Okay, so you have a small set that claims to be a Kakeya set. Using the previous lemma, you have constructed a low degree polynomial that vanishes on this entire set. So you plug in into this polynomial, you plug in any point from K, the polynomial becomes 0. Yeah, that's what we have. Okay, so this is just restating what we just said. So suppose I reorganize my polynomial in terms of degree. So P0 is the collection of constant terms, P1 is all the degree 1 monomials and so on, right? So PD is whatever, the highest degree, all the terms which have degree D, total degree D, that's collected in PD. Okay, now let's pick your favorite direction U, fix it, okay? And this is K is a Kakeya set, so it has a line in the direction U. And P vanishes on all of K, so in particular, it vanishes on this line, okay? So let's say that this line in direction U is A plus TU, right? And I'm going to plug in A plus TU into this polynomial. So this is a polynomial in T. And this notation was a little confusing for me. So to some of you, this may feel a bit silly, but I'm just going to break down what it means to plug in A plus TU into the polynomial P using like a concrete random example. Okay, so this is just to make sure that we are on the same page with respect to notation. So suppose again that, n is 2. So we are looking at a polynomial in 2 variables. Let's say it's some stupid polynomial that vanishes on the Kakeya set K, supposedly. So don't worry too much about it. I just made up this polynomial, so that's not important. I'm just using this to clarify notation, just in case anyone else found it confusing like I did. So now we have this line, A plus TU, right? So, so T varies over 0, 1, 2, 3, 4. And A is, the line is parameterized by these two vectors, A and U. We assume U is a non-zero vector just so that the line is non-trivial, right? So otherwise the line is just E, which, yeah, we don't want to look at those degenerate cases, right? So that's why the minus 0, 0. Okay, so this is our line. So our line is a collection of, how many points? It's a collection of Q points, in this case, 5 points. We're going to get 1 point for every value of T, right? So this is our entire line. We've seen examples of these lines. Those were the red dots that were highlighted a few minutes ago, right? So this is our line. Now, what is P of A plus TU? What does this mean? So this is, well, a polynomial in well, we're going to think of t as a variable. So what is a plus tu? That's really two things here. One is a1 plus tu1, and the other component of this is a2 plus tu2. Okay, so any guesses on, so p is a polynomial in x1, x2. So when I say, well, let's plug in a plus tu, what value do you think x1 will take and what value will x2 take? Given that this is a vector which has two things. At least I'm glad I'm not the only one who found the notation confusing in the book for a bit. Okay, all right. So let's see. So a plus tu is, well, in general, it's actually a vector in Fn, but we are working with F2 right now. So this vector has two components. The first component of this vector is a1 plus tu1. Okay, so these are all the realizations of this, right? a1 plus u1, a1 plus 2u1, a1 plus 3u1, a1 plus 4u1. All of that is basically a1 plus tu1, and we are pulling out, I mean, we are instantiating t in different ways to get this whole line, right? But yeah, so that's the first component of this vector. And the second component of the vector is a2 plus tu2. So when I say p of a plus tu, what I really mean is that for x1, I'm going to plug in the value a plus tu1. And for x2, I'm going to plug in the value a2 plus tu2. Does this make sense? Notationally, give me a +1 if this is okay. All right, very cool. So, so if I was to actually plug this in, this is what I would get. So x1 is a1 plus tu1, x2 is a2 plus tu2. So that's my first term here. My second term is x1 squared. The third term is x2 squared, blah, blah, blah. Now this is the total degree of the polynomial p in this example is 7. So I want to ask myself, what is the coefficient of t raised to 7? It turns out that this will be useful in the argument later. So it's not just a completely frivolous question, just to get some practice maybe. So notice that this is the high degree term. And this is a product of 7 little terms, right? And if I had to push the degree of t to 7, what's the product that gives me that degree? And what's the coefficient of t raised to 7? Any guesses on this one? I'll write this out in full, if you like. That's something like a1 plus t u1, a1 plus t u1, a2 plus t u2. That repeats 5 times. So if I had to get a t raised to 7 term, I would have to, as somebody has pointed out in the chat, I think Krishna, thank you. I would have to make this choice from each of my terms to have any hope of getting t raised to 7, right? So the coefficient would then be u1 picked twice and u2 picked 5 times. So u1 squared and u2 raised to 5. Thanks very much. That's kind of the sanity check that I wanted. So that's very helpful. So indeed, the coefficient of t raised to 7 is this product of some of the u terms. And my point is that that's going to be the case in general as well. When you plug in p of a plus tu into this polynomial, and you try to look for what's the coefficient of t raised to d, where d is the degree of the polynomial p, you're basically going to be stuck with, a bunch of the UIs. There is no room for any of the AIs to come in, because whenever the AIs come in, they kill the degree. Does that make sense? So to get the highest order term, it's going to be a polynomial in just the UIs. Is that fair? Give me a +1 if that makes sense. It worked out that way in this example, but I'm saying it's not specific to this example, because whenever you try to pull out the highest degree term, you have to always make the choice where you have the U partner. You cannot be messing around with the AIs. That's a very sort of informal way of saying it, but hopefully it makes sense. Yeah, awesome. Thank you. All right, great. So then, okay. So then we're in business because, okay, we have this polynomial that vanishes on the line. It's a polynomial of degree at most q minus 1 in t. Why is it a polynomial of degree at most q minus 1? Because we know that p is a polynomial of degree at most q minus 1. So when you plug in, when you plug in these values like we just did, t is going to also manifest as the degree of t is basically going to match the degree of the polynomial, right? So this is now a polynomial in t. And if you think about it a little bit, you should be convinced that the degree of t matches with the total degree of the polynomial p. Because if you go back here and look at what happened, that's essentially, you look at where are you getting that degree d from for the polynomial p, and you're getting it by multiplying out a bunch of the xi's. And each of the xi's now have transformed into some a plus tu kind of term. So now the t's multiply out in pretty much the same way that x's were multiplying out, but except now they've been you can lose the indices and you get a uniform, you just carry forward the t. So yeah, it's a really awkward way of saying it, but hopefully it's clear that the degree of the polynomial after you plug in a plus tu matches the degree of the base polynomial that we started out with. And now the other claim is that it has q roots. Why does it have q roots? The answer is kind of in the previous slide. We know that it vanishes for all t in fq, right? And the number of choices of t in fq is q, right? So we have q roots, degree q minus 1. So the only way that's going to happen is if this is the zero polynomial. Does that make sense? Give me a +1 if this makes sense. Because now we'll be almost there if we are good with this. So this polynomial is this polynomial, which we got by plugging in a plus tu into the original polynomial p. This is the zero polynomial. But if this is the zero polynomial, okay, thank you. If this is the zero polynomial, then what can we say about the coefficient of x raised to d? T raised to d, sorry. Yeah, 0, exactly. Because this is a zero polynomial. It's a polynomial in a single variable now, t. It is the zero polynomial. So the coefficient of t raised to d is 0. But we know that this coefficient was basically this guy with u plugged in, right? So these are the order, whatever, degree d terms. And we plugged in u, and we know that this fellow here is not the identically zero polynomial, because if this was the identically zero polynomial, then p would not be a degree d. It would not be a degree d polynomial, right? Because pd does not survive. Okay, so yeah, the point is that the coefficient of t raised to d in p is basically just pick out the degree d terms, okay, and plug in wherever you see xi, plug in ui. That's basically the coefficient of t raised to d. But this cannot be the zero polynomial, because if this is the zero polynomial, then p did not have degree d, right? So pd of u, which is just xi's being replaced by ui's, that's not the zero polynomial. However, we do know that if you pick any u, pdu is 0, and that is true because there's nothing special about u, right? You can fix any direction. This is a Kakeya set. It's supposed to have a line in every direction. So we can make the same argument for every direction that's available to us. And we will conclude that PD with U plugged in is 0 for, yeah, so maybe here it's misleading for me to say that we have U plugged in. What I mean is PD as a polynomial is not the identically zero polynomial. These are the higher order terms in P, and they cannot all basically vanish on P because that would contradict the degree of P. But what we do know is that PD of U is 0 for all U, and this should already start feeling a bit suspect because, okay, maybe I should just spill the beans. So PD is a polynomial which takes 0 at every point in Fn, which means it's 0 at a lot of places. But if you remember yesterday, the main takeaway of the Schwartz-Zippel lemma was that if a polynomial is 0 very, very frequently, then it must in fact be the 0 polynomial. And Schwartz-Zippel said this even for the multivariate case. So that is our contradiction. So yesterday we saw this. We saw that if you have a non-zero polynomial of degree d, then it can only vanish on a limited number of points. It vanishes more often than that, then it's actually the 0 polynomial. So you're not allowed to vanish on size of f to the n. In this case, this is going to be q to the n. You're not allowed to vanish on q to the n points. Yeah, so that's our contradiction. At a high level, does this make sense? Basically, we got hold of a polynomial. If the Kakeya set is small, we have a suitable low degree polynomial which vanishes on the entire set. And we kind of used that to basically contradict the idea that, okay, if we know that there's a portion of this polynomial which we know is not the 0 polynomial, but because it's vanishing on the entire set K, we can use that to argue that it's vanishing too often, suspiciously often compared to what it's allowed to. As a non-zero polynomial, it's not allowed to vanish so often, and that's the contradiction. Okay, so if all this makes sense, then I'll move on and try to prove the technical lemma that we used, because this whole proof started out by saying pick a polynomial that vanishes on the on K, and pick a low degree polynomial that vanishes on the set K. That was the starting point. So yeah, and it's important that we have a bounded degree polynomial, right? Because that's what we used to argue that we must have a 0 polynomial here, and the fact that P of A plus TU is the 0 polynomial allowed us to say that these coefficients are 0, which is basically what gave us the coefficient of T to the D, which is PD is 0, and that gave us our final contradiction. Okay, yeah, so I don't know if I said it cleanly, but it actually did feel like a kind of clean argument. And there are like slight variations of this in terms of how it's presented. I've mostly remained faithful to how it's said in the miniature, but I think there are other proofs with small variations where you basically show term by term that each of these guys is 0, and you recover that this is a 0 polynomial, but you started by saying that P is a non-zero polynomial. So that's another kind of contradiction that you can get. So there's some superficial differences to how the final contradiction is arrived at. I think it's a couple of other variations and extensions, but I'll not even attempt talking about it because it's not something that I have off the top of my head. But this is I thought it was neat that they got the final contradiction like this, because it ties into something that we learned yesterday, and maybe that was the idea. Okay, so give me a +1 if we can now go and quickly look at the lemma and hopefully finish before the hour. But yeah, no pressure. If something is not clear, then please let me know. I'm happy to attempt repeating any part of this. Yeah, okay. I mean, thank you. What I hope is clear is that it's really a tight argument, as in we really did use everything. We use that, it's a Kakeya set, so there are lines in every direction. We use that the lemma gives us a polynomial that vanishes everywhere. We use the vanishing act multiple times to argue that you have a non-zero polynomial that's vanishing suspiciously often, and that's what gave us the final contradiction. Okay. All right, so now I'm going to just move on to this lemma, which basically is saying that if I have a small number of points, I have a low degree polynomial that vanishes on all of those points. And this is again just a thing about setting up a system of equations which has a non-trivial solution. So let's write down, so we want to come up with a polynomial of degree at most d. So let's write down the most generic degree at most d polynomial. So pull out all your guns, write down all the terms that you can, which is to say, look at all the ways in which you can write down monomials that have total degree at most d and give them a coefficient. Okay, and we have seen this before in terms of, so this is a generic polynomial, and because we have written down literally every single term, the number of terms that we have is d plus n choose n. We have seen this before manifesting as a balls and bins argument. This is basically, if you want the alpha i's to sum to d, and there are n of them, that's like throwing, I don't know, d balls into n boxes or something to this effect, n or n plus 1 boxes, because it's at most d. So you want to have a waste basket, which, if your degree is smaller than d, then the waste basket captures the degree that you're not using. So yeah, this is basically the number of ways in which you can throw d balls into n plus 1 labeled boxes. And that's a standard stars and bars or balls and bins argument. So I will not bore you with that again, but basically the number of coefficients that you get here is d plus n choose n. And that again might ring a bell because this expression is also there in the statement of the lemma, and we'll see the connection in just a minute. So basically, we want that this polynomial vanishes on each of these points, right? So what does that mean? Let me take the first point, a1, and plug it into my generic polynomial, right? So I will substitute x1 equals the first coordinate of a1, x2 equals the second coordinate of a1, and so on. a1 is a point in Fn. It has n coordinates. So I can just evaluate this polynomial at a1. So I will write x1 equals a1, a1, 1, xn equals a1n, right? And so I'll get something. I can now treat my coefficients as unknowns because I want to manifest this polynomial, right? I want to construct this polynomial. I don't know what the coefficients are. So I'm going to treat the coefficients as unknown. I'm going to plug in this a1 into x1 through xn. And so what I will get is, these numbers will get fixed as some constant coefficients because I've plugged in the values a11, a12, and so on up to a1n. The coefficients C I'm going to treat as variables. And so I'm just going to say, well, okay, I want this to be equal to 0 because I want this polynomial to vanish on this point. So I get one constraint from a1. I do the same exercise for a2, I get one more constraint. I do the same exercise for a3, I get one more constraint, and so on. I go all the way up to an, and now I have a collection of capital N many constraints, but n is strictly less than d plus n choose n. And the number of variables I have is exactly d plus n choose n. So this is a system of homogeneous linear equations, which has more unknowns than equations or constraints, right? So this is a, what is it called? Underdetermined or whatever. I have more variables, less constraints. That sounds like a good thing to have. And so this is a situation where we do have a non-trivial solution. So therefore I can manifest these coefficients and come up with this polynomial, which has the promised property that it vanishes at all the stipulated points. So every point that has been given to me as a specification saying, I want this polynomial to vanish here, here, and here, each of those locations in Fn manifest as an equation in my system of linear equations, but the number of points is chosen carefully to be less than the number of coefficients that I'm going to see here. So so I have, like I said, fewer equations than unknowns, and therefore I will be able to come up with a set of coefficients that actually works. And so we have designed, in fact, a polynomial whose degree is at most d, and which is such that it vanishes everywhere that we require it to vanish. And this is the polynomial that we go back and plug into our argument here. So yeah, that's about it. That's all that I had to say. And yeah, maybe, I don't know if it's a function of me gulping down a lot of stuff, but for a change, we're actually mildly under the hour. So yeah, let me know if you have questions or comments, especially I didn't explicitly ask if the last lemma made sense. So let me know if it did or if it did not. And this is probably also a good time for closing comments. Vinay, did you have any thoughts?
Yeah, I think we finished before 11.
Indeed. Yes. Yeah, it's a bit. Yeah, I mean, I'm a bit surprised, but I think this is, like I said, largely a function of my choosing not to get into a lot of the backstory. The backstory is very rich, and there's a lot going on. So please do explore that. There's a whole section in the miniature where they've described this construction, which tells you why there are no lower bounds on Kakeya sets in the Euclidean setting. That's something that, that's something that I didn't delve into at all. But it exists. And I think there are some philosophical musings about why doesn't this carry over to the finite field setting? And some people think it's just, I don't know, the discretization making things messier. Some people say there isn't a smooth notion of distance in finite fields. I don't even know what that means, but I read that in one of the articles that I was looking up while preparing. So I'm going to try and go back and make a little more sense of some of the things that we saw. But just as a standalone proof, admittedly, I don't have a whole lot of intuition for what lines and directions and such things mean in the finite field setting. So I think we've gotten ourselves a few little exercises in terms of food for thought. But hopefully at a super high level, things are holding up or adding up or whatever. Cool. Okay. So then I think just to...
Yeah, so one comment I would make is I think several of these problems are open, I think, because this technique that you mentioned, which is the polynomial method, which is looking at a multivariate polynomial and saying if the degree is not too large, then it can't have too many zeros, right? That somehow, I think, somehow missing in the that at least mathematicians are not using it as part of their toolkit, and somehow all of these things came from computer science, and in particular, this proof also came from somebody who works in arithmetic complexity. I think Dwyer. I don't know if you mentioned the name, but
I didn't actually. Yeah, you're right. It's Dwyer. Yeah, and it's a nice, cute.
So it was around 2007, 8, something like that.
Right.
And yeah, so it is. I think shows the increasing power of simple combinatorial tools, and the fact that they can be exploited so powerfully. I think that is the story, I think.
Oh, yeah, absolutely. Yeah, I think, yeah, I mean, I guess, I don't know, there's some of the simplicity in retrospect vibe going on here, but yeah, I still thought it was quite, I mean, it was both elegant, but also very clever at the same time somehow. And yeah, I guess it's maybe worth spending some time with just, yeah, I think it's a good exercise to check that everything is really tight. I think none of the assumptions can be loosened. I mean, at least in this proof locally, at least it's evident that we really throw in the full weight of all the assumptions that are being made here. But I think perhaps there have since been some tightening of these bounds and so on. But this proof, as it were, I don't think there's a lot of slack in this argument here. So and everything holds up nicely. Yeah, so the main takeaway, as Vinay just said, the polynomial method, working with a small set, try to see if you can find a polynomial that vanishes on that set and exploit it. And keep in mind that as far as multivariate polynomials go, if you're non-zero, you can't afford to vanish too often. So those two things kind of combine to give you the tension that you need to prove the contradiction that you want. Yeah. So yeah, I thought it was a pretty proof at the end of the day, in spite of not having a lot of geometric intuition over finite fields, but nonetheless, if you take the definitions as a given, the details seem to check out. So that's where I leave it. Tomorrow we come back for something. I don't off the top of my head remember what the next one is about, but we'll be back tomorrow at 10 p.m. to talk more. So thanks so much, everyone, for sticking it out. See you tomorrow then. Good night.